Now it's my pleasure to introduce our first speaker, Dr. Parker MacCready, who will be talking about the underwater Amazon of Puget Sound. As a professor of oceanography at the University of Washington, Dr. MacCready works to advance fundamental understanding of estuaries and coastal physical oceanography. Tonight, he is going to talk about how the interaction of tides, rivers, and ocean gives rise to a vast and persistent deep current of nutrient-rich water that sustains fish and marine mammals in Puget Sound. Okay, I'm going to pass it over now to Dr. MacCready.
Thanks very much. I hope you all can hear me, and it's exciting to be here. And I think my talk is going to be a little bit of physics, because that's what she said. I'm a physical oceanographer, so I study the physics of currents and mixing and so on, especially in estuaries and coasts, and especially around our estuary, the big Salish Sea, which I find to be a pretty exciting place. I won't be talking, I'll talk somewhat about things that influence the ecosystem. I won't be really telling you about benthic organisms, but you can put the pieces together, and hopefully you'll know a little more about that when I'm done. So I'm going to start my presentation. This title of this is The Underwater Amazon of Puget Sound. It really should be the whole Salish Sea, because that's really what I'm going to talk about. I'm at the University of Washington in the School of Oceanography. I'm part of what's called the UW Coastal Modeling Group. There's a couple of postdocs, Jillian Xiong and Kate Hewitt, and 3 current graduate students, although Erin Broach just graduated with her PhD. She's a Canadian. I think she's escaped back to Vancouver. So congratulations to her. Anyway, and you can see a satellite photo of the Salish Sea with the Strait of Georgia right down here, and Strait of Juan de Fuca. We'll show some other maps. Oops. Okay, so I am gonna introduce this topic of like, what are the patterns of water movement in the Salish Sea? And in this thing at the right, it's a map of the region. So up here is Strait of Georgia. Down here is Puget Sound. I hope you can all see my mouse. Sheila, can you see my mouse? Like my, like my cursor? Is it moving around on the screen?
Yes, we can.
Okay.
Yes.
Thanks.
Yeah.
Thanks, just checking.
Good.
So I'm gonna, we use a lot of observations, but we also do computer modeling of this region. We simulate it using a big 3-dimensional model. And I'm going to show some results from that here and in a few other slides. But what is going to be in this map here, you can see this patch of sort of orangey colored water, orangey colored points. And that's where I have put a bunch of particles, like pieces of water, basically, and marked them in the model. And then I'm going to follow them for a month. And underneath them, there's some blue water that's deeper. So the pinky ones stay near the surface and the blue ones stay near the bottom. And we're going to follow them for about a month. And so now it's going, hopefully, you can see they're sort of wiggling back and forth. And that is the tides. The tides, the tides go up and down, up and down. But in order to do that, they have to move water back and forth. And that's the strong tidal currents we see here. And then as this movie goes on and on, you see there's progressively a big separation of the surface water, which is the orangey pink dots, and the deep water, which is those blue dots. You can see over the course of a month, the blue dots, almost all of them, moved into the Salish Sea. They moved in through Harrow Strait, filled up Strait of Georgia. They're oozing into Puget Sound, into Hood Canal, over Admiralty Inlet, but they're persistently moving landward. And that's all the deep water, remember? And then almost all of the shallow ones, these pink ones, they scooted out to the coast. Even though they started out in the same, the same location, they went very different places. And that is the underwater Amazon that I'm going to talk about. This fanciful title, the Amazon. It's not about the online retailer. It's not about the mythological race of women warriors. It is about it's a comparison to the Amazon River. And that in particular, not to the depth of the Amazon River, but to the flow of water in the Amazon River, which, as we know, is the biggest river in the world. And but this water flowing in that persistently pulled all these blue deep dots in is it's a big amount of water flowing in. I want to really emphasize how amazing this is in terms of wonders of the Salish Sea. This is a wonder. Like, I wonder how it happened. In fact, I've spent my whole career studying this. It's so wonderful. But the size of this inflow that dragged all these blue dots in and splooshed them into the Salish Sea, it's about 70% of the size of the Amazon River, but it's flowing in the wrong direction, right? It's going towards the land. It's going from the ocean towards the land, and it's really big. Another way to think of how big it is that it is about this inflows, persistent inflow, which happens all year round, and it's like 20 times bigger than the sum of all our rivers. So our rivers, the big one is the Fraser River. It's about 60% of all the rivers in the whole Salish Sea, but all the ones that in Puget Sound add up to some more, and so on. There's lots and lots of rivers, but they're still tiny, just like 5% of the size of this deep inflow. And so, as you can imagine, this deep inflow has a huge influence on water properties throughout the Salish Sea because it is filling our system and flushing it with ocean water constantly and persistently. Every few months, all the water, depending on exactly where you are, all the water is replaced by ocean water. And that's why, for example, our water is so salty and cold is because even though rivers keep dumping in and the sun keeps shining down on it, you keep replacing it with this cold, salty ocean water. And that has a lot of important ecosystem consequences as well. So let's keep moving. Okay, so this pattern that I've described of a deep inflow is something called the exchange flow or the estuarine exchange flow, because as you saw in that first movie, it is an exchange of water. The surface water is going out and the deep water is coming in. In fact, because if that much water was coming in and it's enough to fill up the whole Salish Sea in 3 months, almost the same amount of water had to go out. And so that's why we call it an exchange flow. This pattern, and there's this diagram with the light blue arrows here is a cross section of a really simplified estuary, and it shows this pattern of deep inflow that sort of moves up and then joins the shallower outflow. And along with that, there's a typical pattern of salinity. That is how salty an estuary is, with salty ocean water toward the ocean and fresher water toward the river end. And then some what we call vertical stratification, meaning that at any location you look at, it's saltier near the bottom and fresher near the surface. That means it's stratified and it resists mixing unless you push it around with tides. I won't go into it with much detail, but I have 5 different cross sections of salinity in estuaries around the United States. And they all have similar patterns or variations on this pattern. The big one is the Chesapeake. I'll point out some of the scales of, I don't know why that did that. Okay. Just to remind people of how big the Salish Sea is, it's because it was scoured out by glaciers, it's really deep. It's like hundreds of meters deep, sort of 200 meters deep through most of Puget Sound, over 300 meters deep in the Strait of Georgia. And so it's a big amount of water. So continuing. So here's the an explanation of why on Earth there should be an exchange flow. This exchange flow requires a river and tidal mixing. And so it has a source of fresh water somewhere in the system, which is less dense and lighter than ocean water. And then, of course, it has an ocean sitting out there just ready to fill up the whole thing with ocean water if it gets a chance. But the rivers push back. So there's just a little thought model that you can use to understand how the exchange flow keeps working. That is, if I just start off in this cross section at the top and I have some fresh water coming in with the river, but no mixing at all, it's just going to sort of glide out on top of the salty ocean water and be a thin layer going slowly out. But then I'm going to add the other ingredient that is very important around here and in estuaries all over the world, which is mixing. That is these curly arrows, which mean turbulent mixing. This is caused by tides. The tides move back and forth across our very rough bathymetry. And there's big variations of currents, especially in the intense places like Harrow Strait or Admiralty Inlet or Deception Pass, San Juan Channel, Cattle Pass, all of those. If you've been out in a small boat, you see the surface of the water sort of boiling sometimes, and it has really big patterns of ripples and smooth places, and that is the signature of this tidal mixing. What that does to the salinity pattern is it mixes the fresh water down and the salty water up. So now these surfaces of constant salinity are more vertically up and down. But now remember, it's salty on this end and fresh on this end. Gravity doesn't like that. It wants to fold the whole thing over and flatten it out again, because that's, gravity wants to do that. And that's what's shown happening in the last diagram. And as a consequence of that, you have to pull in ocean water and send out mixed water. It's a mixture of mostly ocean water and some fresh water. So that's the conceptual diagram of how the estuarine exchange flow works. There's a lot of reasons to care about the estuarine exchange flow, because as I said, it happens in estuaries all over the world, big and small, and in fjords. And so it's an important part of the melting of glaciers that come into fjords, which could contribute to global sea level rise. So in that case, often the water from the neighboring ocean is warmer and it flows in, but then it melts. It exchanges with well, it brings it in and actually melts the face of the glacier, and then the cold water goes back out. Again, the density part is mostly driven by salinity here, but the temperature effects are really important. Getting a little closer to home, here's some sort of an infographic from the Washington State Department of Ecology related to sewage treatment. And one thing my group works on is the effects of treated sewage. We work with Susan Allen's group at UBC and other groups down in the Puget Sound as well. So as they point out, excess nutrients are a problem in Puget Sound or lots of estuaries. And so we put in nutrients. Now, when I say nutrient, it means like fertilizer for plants. It's usually in the form of nitrate or ammonium, which is the limiting nutrient for the growth of phytoplankton, our main photosynthetic organism here. And one place it comes from is sewage treatment plants. And that can cause, it grows algae or phytoplankton. Here they're showing it as benthic organisms, but mainly what it grows here is phytoplankton. And that increases the oxygen in the surface water where phytoplankton are growing, where photosynthesis is happening. But then the phytoplankton die, they sink down to the bottom, and they are like a giant compost heap. They are sort of, bacteria eat them. And along the way, the bacteria use up the oxygen in the water and give off, actually they release the nitrate back into the water. So if the if the oxygen gets too low in the deep water, that causes stress on benthic organisms. So that's a common story around here and in estuaries everywhere. It's like that's the cause of hypoxia in Hood Canal, for example. So I want to talk a little bit about the numerical model we use for this, because it's kind of an interesting resource, and it's what my group does, is build this thing and run it. And so just reminding you, this result that I showed where the particles moved around, this was all done in a computer simulation. This is not data. We actually do sometimes put out physical drifters in the physical ocean and follow them with their GPS trackers. But this is all done using simulated particles. So next. Okay. The computer model we use is something called live ocean. And you can see a figure from the live ocean domain on the right. This is the whole region that's covered by the model. So it's all of Oregon, Washington, a lot of British Columbia, including all of Vancouver Island, a lot of the coastal waters off into the abyssal Pacific Ocean, and then the inland waters of Puget Sound and Strait of Georgia. I gotta move this thing over. Strait of Juan de Fuca, and the main connection of the whole Salish Sea is what we call this place, as I hope you know. The main connection is through the Strait of Juan de Fuca, although there's a smaller connection through Johnstone Strait to the north. And that is constantly feeding in water to the system, as I said. So this is all these colors out in the ocean. That's sea surface temperature on a certain day, simulated by the model. The model is three-dimensional, it has all the layers, it's realistic, has tides and winds and rivers and atmospheric heating, has at this point almost 300 rivers and wastewater treatment plants and so on. And it tries to be as realistic as possible. We make long hindcasts, like decade-long hindcasts for scientific purposes. We also make a daily 3-day forecast. So here's a little sketch of how that works and where you can go to look at results. We take in information from like an atmospheric model, like a weather forecast model, and about surface heating and rain and stuff like that, and winds especially. We get an estimation of the state of the actual ocean beyond the model domain, so in its open boundaries to the south, west, and north, from a global model that is run by, in this case, the Navy of the United States, and although there's various sources for models like this, and it runs in real time a daily forecast. It does something called data assimilation, so it takes observations and keeps pushing the model back to be real, or as realistic as possible, very similar to what weather forecasts do these days. So that's why the weather forecast is as good as it is. As I said, we use lots of rivers. These are from river gauges, for example, the Fraser River here, and it has tides. So then that all goes as information at the edges, forcing this three-dimensional computer simulation, which is really just, it's solving the equations of physics and some biology and chemistry using a computer, just sort of marching it forward in time, 3 days at a time in this case. And then we do a bunch of processing of the output and send it to several places, in particular the Nanus MVS, which I'll show in a second, and the Live Ocean website. And that's where you can look at it. So the Live Ocean website is the one I maintain. If you just search in Google or whatever for the word Live Ocean with no spaces, you'll get right there. And you'll come to this page, and it has some buttons for like daily forecasts and various pictures, cool background information about how tides work. In case you're interested in tides, there's some pretty interesting information, how the model works, how we test it. Anyway, try clicking on some of those buttons. You might find something you're interested in. And next, but the other button you can look at is the Nanus NVS. Nanus is a regional organization of the Integrated Ocean Observing System, and they integrate lots of scientific research and products from around this whole region and put them in a place that you can look at it, including Canadian data and US data. So here is the NANUS MVS. NVS stands for NANUS Visualization System. But in the screen I'm showing you, it brings together fields from live ocean. In this case, it's a map view of surface temperature, but you can look at it at different depths and different times, all for the most recent forecast. And then there's all these little things that look like tiny, space capsules or whatever, or video game characters. And each one of those represents an actual physical observation that is reporting back in real time. So like a mooring out in the water, that's measuring temperature in real time and sending it back by radio to the to land, and then it gets integrated into the system. And you can actually, by going to this site, you can compare the model output which is these red lines down here as a time series of temperature, to the observations up to the present. Anyway, it's a cool system, but there's so much to it that I'm not going to describe it all, but it's an incredible resource if you don't already use it. Just a little bit about how we test the model. I described how we make it, but we also spend about half of our effort making sure that it's any good, that it's actually simulating the patterns of currents and temperature and salinity and also chemistry. And so one place you can actually look at that, well, what we do is we gather together all the observations we can find from many different sources. And, because there's lots of groups out there, Canadian groups, US groups, the State Department of Ecology, the Olympic Coast National Marine Sanctuary, it goes on and on. And we put all their observations in a single format and then compare them one-to-one with the model. So we routinely, as we make model developments, make plots like this, where there's the x-axis means observed, and all the dots mean, one observation at a place and a time that, for example, a ship went and dropped an instrument overboard and measured the temperature. And then the modeled is the right. If the model was exactly the same as the observations, that would be along this one-to-one line. And so we do this, in this case, for salinity, temperature, oxygen, nitrate, dissolved inorganic carbon, and alkalinity. These are carbon variables associated with ocean acidification. And you can actually interactively explore different parts of these data sets and our comparison using this model versus observation viewer. But in general, for the purpose of this talk, you can just assume the model is doing kind of what the real world is doing. It does it better for temperature and salinity, and it has a harder job with biogeochemical fields like nitrate and oxygen. You can see there's more scatter here. Okay, back to the exchange flow, my favorite subject, because I'm a physical oceanographer. So hopefully this is about the most sort of confusing data plot I'm going to show. But I just want to clue you into the pattern of what the exchange flow looks like a little more clearly than the dots moving around. We use the model simulation and look at a bunch of these cross sections like JDF1, JDF2, that stand for Juan de Fuca section 1, Juan de Fuca section 2, and up into the Strait of Georgia and down into Puget Sound. And we calculate the strength of the exchange flow, in this case averaged over a whole year, and then plot it versus distance. So the x-axis in this plot, the top plot A, is distance, and the y-axis is what I'm calling Q in, and that is the volume transport of the exchange flow. So it's the inflow. It's this underwater Amazon that of the title of this talk. And it tells you at the mouth of the Strait of Juan de Fuca, it's about 140,000 cubic meters per second flowing in, and a very similar amount flowing out above it. The exchange flow gets smaller. The exchange flow gets smaller as you move into the system, into the Strait of Georgia, smaller still in Puget Sound. That's this red line here. Nonetheless, even in Puget Sound, as you go over Admiralty Inlet, the strength of the exchange flow, which is about 40,000 cubic meters per second, is something like 20 times the size of all the rivers flowing into Puget Sound. So it's still an overwhelmingly important circulation pattern. I'll also point out that this inflow, well, I'm gonna wait on that. One question that I look at a lot is what controls the exact size of this transport. Why is it nearly the size of the Amazon River? Why isn't it some other number? And that's what I study as a physicist. We recently came out with a paper that we think has some answers about that. It has a surprising relation to the tides, but I won't really go into those theories because that's a different talk. That exchange flow, it appears in the model, but it also is quite well represented in observations. So it's really there. And these are observations made by Rick Thompson, Canadian oceanographer, and who put out a bunch of instruments across the Strait of Juan de Fuca at this section here, and then left them out for a long enough time to see, like, well, what were the currents doing at different depths? And the results look kind of like this. So this darn it, this bottom panel here is a cross section. So this is distance across the Strait of Juan de Fuca, and the y-axis is depth in meters. So you can see, as I said before, this is a deep system, 200 meters deep. Lots of estuaries are much shallower, so we can be proud of that. And then the colors, this sort of heat map or contour plots, show the pattern of speed in centimeters per second averaged over some long period of time of the inflow in the deep water of the estuarine exchange flow and the outflow in the thinner surface layer. So the greenish waters going in, the bluish waters heading out. So this is what's observed. Interestingly, there are times when the whole pattern changes. This is times during the winter, big storms like we just had, or maybe you're having it up there right now, but we had a huge rainstorm here in Olympia today. And then the water from the Columbia River plume comes out, heads right up the coast, and turns the corner and goes around it at Neah Bay and turns the corner and heads in the Strait of Juan de Fuca. And that's this big red panel that happened. In this case, it was observed in December of 2002. Okay, so just an interesting side note that. Now, getting onto the ecosystem consequences of this in the last 15 minutes of my talk. If we go off in the water of the Northeast Pacific, we call it the Pacific Northwest, but from the ocean's point of view, it's the Northeast Pacific. And we just look at observations. So a ship went out and went to station 31 and lowered an instrument package down to, in almost 3,000 meters of water, which is how deep the ocean is out there, and then measured a couple of things. And so one thing it measured is nitrate, which, as I said, is the important nutrient driving phytoplankton growth. And the other is oxygen. And so this, looking at the panel of nitrate, x-axis is nitrate concentration. Just know that 40 is kind of high. And then the depth, or z coordinate, is on the y-axis. And so you can see the nitrate's really low near the surface. The reason for that is that phytoplankton are always just eating up nitrate as fast as they can. They use up all the nitrates. As long as the sun is shining, they're going to use up all the nitrate. So it gets drawn down here. But in the deep water, it's very high. And along with that, the surface water the oxygen levels are relatively high. That's because of photosynthesis and exchange with the atmosphere, because there's tons of oxygen in the atmosphere compared to the ocean. But down below, at 500 meters depth, you see the nitrate is really high and the oxygen is really low. And that is a consequence of the global pattern of circulation of water that takes like 1,000 years. The water down there in the bottom of the Pacific might have last seen the atmosphere, well, depending on exactly where you are, it could have, it was hundreds and hundreds of years ago. And it could have been off, could have been in the, well, off Russia, it could have been, off the coast of Antarctica, but it sank down to the bottom of the ocean and it's been wandering around for, centuries since then, finally finding its way to the Northeast Pacific, which is kind of the end of the global overturning circulation, or it's one end of it. And the water's really old. And along the way, that same pattern I described of organic particles from photosynthesis, like dead phytoplankton, sinking down and being turned back into nitrate while using up oxygen. This high nitrate here is the accumulated result of all that organic matter, what we call remineralization, and for centuries. And that, so there's almost no oxygen left at depth in the Northeast Pacific. Now, why am I talking about the Northeast Pacific when this is a Salish Sea talk? Because of the estuarine exchange flow. It is dragging in water from the Pacific that's coming from depths here around 200 meters. So it has pretty high nitrate and it has relatively low oxygen, depending on exactly which depth it's able to source. And so that's extremely important. The nitrate, I mentioned, it comes from wastewater treatment plants, and other human activities, but it overwhelmingly comes from the ocean. So entering into the Salish Sea, 95% of the nitrate is coming in from the ocean. That's a pretty, so to the extent that nitrate drives photosynthesis and biological productivity and the feeding, the zooplankton eat the phytoplankton, and the fish eat the zooplankton, and the orcas eat them and whatever, and then we eat the salmon too. All of that is driven largely by this exchange flow, the deep inflow of nitrate that gets mixed up by tides into the surface water, allows photosynthesis, high productivity in the whole Salish Sea. I'll show a cool movie of that right at the end. But the fact of the combination of what the chemistry of the ocean is matters so much. Interestingly, in other estuaries, like say the Chesapeake, another big one in the United States, the situation's absolutely the reverse. The major source of nutrients is the land there. It's all those pig and chicken farms up in the Susquehanna River coming in. And the ocean is a relatively small source of nitrate. So very different. I'll just show some pictures of observations of these chemical patterns. This is from data taken in a section that goes along the Strait of Juan de Fuca and through Admiralty Inlet and into either Hood Canal or Puget Sound. And so these are more cross sections. Let's just focus on the ones on the right, E, F, G, and H. Again, the x-axis is distance along the transect. And I stress these are observations. I'll show a model result right after this. But you can see these patterns playing out in the Salish Sea. So, for all these y-axis is depth down to like 300 meters. And so out in the left part of this plot, that's on the coast coming into the Strait of Juan de Fuca, going over shallow, very active Admiralty Inlet, and then dumping into Hood Canal, which is rather stagnant and has a long residence time. You can see the salinity is high coming in because that's where the salt comes from. It doesn't come from the rivers. Gets mixed in a little bit with the river water here, this purplish stuff. But these numbers, like it's coming in at what's called 34, that's 34 grams per kilogram of salt. And it only mixes down to like 29 grams per kilogram of salt. So it's still like 90% seawater, roughly. And that's true everywhere here. Again, because the exchange flow is so much bigger than all the rivers. along with this high salinity comes in low oxygen water. That's 50 micromoles per kilogram. That's like hypoxic. 60 is about hypoxia, even though it gets up to 250, which is near saturation because of photosynthesis. And there's some other chemical properties I won't talk about, but it comes in with lower pH and lower something called aragonite saturation state, which is important for oysters. Just a movie of kind of a similar process going on in the model. And this is a movie for a whole year of one of these cross sections. So it starts out on the coast, it's saltier, moving in this case to Hood Canal. And here's nitrate in the middle and then oxygen in the bottom. An interesting thing you'll notice is that, look at the nitrate. It's coming in high, like 35, but then it mixes and it's all relatively low here. And that's because of mixing over the Admiralty Inlet, or it happens in Harrow Strait too, and the San Juan Islands, mixes the low nitrate water from the surface with the high nitrate water below, and you end up with a mixture of the two. But then the nitrate ends up getting concentrated to even higher values in Hood Canal because of the sinking particles, organic particles. That also causes the lowest oxygen water that we observe in Puget Sound is in the head of Hood Canal in the fall. And I think I'm going to wrap this up just showing a movie. This is another model, but it's the same model, but I'm showing a different field, which is phytoplankton. So this is another thing that the model simulates in order to be able to, figure out how much nitrate is there. Let's stop it here. So I'm going to go through the panels. Actually, where do I want to stop? Oh yeah, it looks good. Okay, so the whole model domain is this thing on the left, and this shows us trying to do the best realistic simulation we can of phytoplankton. This is a surface field. Where it's red, that means the phytoplankton is in high concentration because of growth. It's a phytoplankton bloom that happens every summer. And then these bluer values are low phytoplankton, which is typical of the ocean offshore. You can see all along the coast of especially the Washington coast and out here at the mouth of the Strait of Juan de Fuca, very high phytoplankton values at this time. And that's because of that same ocean source of nitrate, but it's something called wind-driven upwelling, where the winds from the north push the surface waters offshore. A little counterintuitive that a wind from the north should push things offshore, but it has to do with the rotation of the Earth, the so-called Coriolis force. Super cool reason to study physics. But when it pushes the surface water off, it drags the deeper water up. That has the same high nitrate source that is coming into the estuarine exchange flow. But on our coast, it only happens during the summer. In the estuarine exchange flow, because it's driven by something different, not by the winds, but by this combination of tides and rivers, it goes all year round, although it only really blooms in the summer when we also have sunlight. So you see phytoplankton bloom here, phytoplankton bloom here in this case, strongest in Puget Sound. This middle map is just a focus on Puget Sound. And then I show a cross section down through Admiralty Inlet, down in Main Basin, through Tacoma Narrows into South Puget Sound. And this is where I live right here. This cross section is shown here. So you can see the phytoplankton bloom is this red thin line at the top. So it's very much concentrated only where the light gets. And in some places it goes deeper, but only because of mixing, not because of phytoplankton growth. So here's Tacoma Narrows, here's Admiralty Inlet. This gray line shows you the state of the tides, whether it's spring or neap tides, and also the state of the wind and the rivers. And so essentially that That's like the whole of my talk, really, is just, ending with this movie, trying to tie together the pieces of circulation, the exchange flow, the source of nutrients, largely from the ocean, and then mixing to the surface because of tidally driven mixing that causes phytoplankton growth and everything that is consequent to that makes the amazing ecosystem we all get to live in.
Well, thank you so much. That was amazing and so much more too. I think a lot of us will be watching it again to get more of the details.
I'm excited to be welcoming Rebecca as a fellow marine invertebrate person. And I would like to just note that the living on the edge, how life thrives in the intertidal is, as you see on the screen, what Rebecca will be talking about. Rebecca is a marine ecologist growing up on Vancouver Island, where she began working as a marine educator in her teens. She pursued a bachelor's and master's degree in marine biology at UBC, focused on the effects of climate change on the intertidal communities of the Strait of Juan de Fuca. Most recently, she has worked as a scientific diver and researcher at Friday Harbor Laboratories, studying bull kelp and the challenges facing kelp forests in this region. I believe she is now back in Vancouver. So tonight, we are very pleased to have Rebecca with us to share her experience and knowledge of organisms that call the intertidal area, where the land meets the sea, their home, and the skills they have adapted to survive in two very different environments, air and water. So welcome, Rebecca, and I'll turn it over to you now.
Thank you so much. So thank you so much to everyone for being here. I'm very excited to chat about this. This, is preparing for this presentation. I was looking for what kind of photos I could use, and I realized that I could go back an entire decade through my photos and find when I first started working as a marine educator at the Shaw Centre for the Salish Sea in Sydney and Victoria, and start to pull those out. And that was a really cool experience. So I've really loved prepping for this talk, and I really hope everyone enjoys it today. So as Sheila introduced, I'm a researcher. I was working at Friday Harbor Labs in the San Juan Islands until very recently, but now I've moved back to Vancouver to work on some more bull kelp stuff. But I'm happy to chat about the intertidal today. We're just going to see if my computer wants to load for me. There we go. I'm speaking to you today from the traditional, ancestral, and unceded territories of the Musqueam, Tsleil-Waututh, and Squamish nations, who, like other Coast Salish nations, as well as the Pacheedaht Nation, the Makah tribes, and the Laikwilta-speaking peoples, have lived in relationship with the lands and water bodies of the Salish Sea region since time immemorial. And it is important to emphasize both lands and waters here, because tonight we are talking about the intertidal, which is right where the land and the sea meet. Specifically, as Sheila mentioned, we're going to talk about what it takes to live here. So the intertidal, it's the area between the highest high tide and the lowest low tide, an area that is sometimes underwater and sometimes out of the water. The width of this area varies a lot just based on the slope of the shore. So in flat, gently sloping areas, you get lots of intertidal area. Think of really long walks on the beach. Other places, like the picture I just showed, you get the shoreline that's just super sheer and you're basically on a cliff and you just have a couple of meters of space to work with. The tide is, of course, what drives this half in, half out situation for the intertidal. This is a really great way to get to follow up on Dr. MacCready's talk. Some of the ideas around tides and exchange will be really useful for understanding how this stuff works. So the tide is the pull of the moon and the sun's gravity on Earth's oceans. And that ends up sloshing the water out in one direction and then the other as the Earth rotates and revolves. What this diagram is showing is a very, very nice theoretical version of what the tides would look like, where everything under this bulge here is the high tide, and then everything under this thin area is the low tide. When we actually look at how tides behave, they're a lot more complicated. When that bulge of water sloshes up against the continents, and when you count for what Dr. MacCready mentioned earlier, the Coriolis effect, the tidal patterns get just a lot wilder. And that means that around the world, there's a lot of variation in terms of how often high tide and low tide are happening. And that's shown in the first map. How high those tides are relative to sea level, that's shown in the second map. And then also when those tides are occurring, those numbers are all relative to Greenwich time, but essentially high tide and low tide hit at different times at different places around the world. So when we talk about the Salish Sea, we have to keep in mind that intertidal environments work differently depending where you are because of these differences in the tides. But really what we care about is the Salish Sea here. So let's focus in. The Salish Sea has mixed semi-diurnal tides. Semi-diurnal just means that we have 2 high tides and 2 low tides in a day. And mixed refers to the fact that those tides are of unequal height. So that means, bear with me here, we have one low tide, one high tide, followed by one high low tide, followed by one low high tide, just for fun. And then it just repeats that all over again. Now, here are some real tidal predictions from Vancouver from this June during the most extreme daytime tides of the year. And just for fun, because of where midnight falls here, you have your higher low tide first and then your lower high tide second. But then you watch and it goes down to this really low tide and it's almost 0 meters, just so that our binational audience is all on the same page. American tide charts work differently than Canadian tide charts. They use different baselines. So in a Canadian tide chart, when you see a tide close to 0 meters, that's pretty much as low it's going to get. There's a couple times you'll get a negative tide, but it's not super common. Versus on American tide charts, this would translate to a negative tide, even though if you did the metric to imperial calculation, nowhere you're going to get that. So just as a heads up, if you're ever wanting to go intertidling in the other country, keep in mind that what the tide measurement tells you will be different to what you're used to. So finishing off on this tide graph, the high tide that you get, the highest tide of the day, is about 4 meters, closer to 5 meters, close to 15 feet. And that's a number that is pretty normal for the Salish Sea, but as I'm going to explain in a little bit, there's variation in what the tides look like within the Salish Sea as well. So when we look across the Salish Sea, what we have to remember is that the Salish Sea is an enclosed basin with just 2 connections to the Pacific Ocean. In case you've forgotten, that's Juan de Fuca Strait in the south, and then Discovery Passage or Johnston Strait in the north, as well as a couple smaller passages. But most of the water moving in and out of the Salish Sea does travel through Juan de Fuca Strait, which means high tide arrives as a wave from Juan de Fuca Strait down through Puget Sound and up through the Strait of Georgia and even into Discovery Passage. Some definitions of the Salish Sea actually use the influence of northward wave coming from the south, that influences where the tides happen. That's actually used to kind of be like, this is where the Salish Sea ends up in the north. So I think that's kind of interesting. But because of this wave pattern, it means that the low tide, which happens around 1 p.m. in Vancouver, will actually happen at 8:30 a.m. at the entrance of the Salish Sea. And I used Vancouver here, but you could equally say this of Seattle and Olympia. It's pretty close, like 12:30, 12:45 down there. So it's a really similar idea of there's a delay between when high or low tide happens at the outer coast and then when it reaches the interior of the Salish Sea. And this actually has consequences for how harsh the intertidal is for intertidal organisms, but I'm going to talk about that later. For now, we're going to go back to what the intertidal environment is like. So Here I have some lovely photos, one from Denman Island, so off of central Vancouver Island, and then one from down off of, well, basically just next to Jericho Beach in Vancouver. And while the tides are the defining physical feature of the intertidal, if you've walked a beach and felt the difference of, yeah, running across sand versus stumbling across rocks, you know that the substrate matters a lot. And for intertidal organisms, that's also true. Living in one of these environments will look very different than living in the other. So, as scientists, we love to make a good chart, we love to make a good gradient, and that's what this is. This shows increasing particle size. So, mud is the finest of the particle size, and then you get to bedrock, which is basically not a particle, it's essentially just the earth, I guess, at that point. But if you're living in mud and sand, it's going to be very different than if you're living on cobble or boulders or bedrock. And that's really going to be important for what your lifestyle is like as an intertidal organism. And of course, the Salish Sea does have a range of these. So I'm going to call out to Padilla Bay or Whitty's Lagoon or Spanish Banks. Hopefully, one of those environments is familiar to you. That's going to be a really sandy environment, and it's going to be very different to stay put there than if you're talking about the bluffs of Lighthouse Park or Ruckle Park or all the way out at Cape Flattery. Now, again, because we love a good chart, if we put this into the methods that organisms use in these environments, in sandy or muddy environments, your best option is to try and stay put in the substrate. So you bury part of yourself in the mud. So, for example, eelgrass will have its roots in the mud, clams will dig themselves down, a crab will bury itself. That's what Dungeness crab do, for example. On the other extreme, in these larger substrate environments with cobble or boulders or bedrock, you're going to live either on top of the bedrock or you might live in the spaces kind of in between or under the boulders. So you're in general on top of the surface. Now, what's kind of interesting is this intermediate environment where you get small rocks packed together or where you get kind of cobbles all piled up on one another. That's actually where you find the fewest species. So that is basically where you don't have the ability to bury yourself because it would be too dangerous if one of those rocks fell on you or those cobbles fell on you, but you also don't have the ability to live on top because those rocks are moving around constantly. So if you ever really feel the need to like send your kids to run around in an environment and you don't want them hurting anything, send them to a nice pile of pebbles and cobbles and they can go wild. So with all of these substrates available to you, that's actually related to how much wave action is going on. And that will also determine how hard it's going to be for you to stay on those substrates. Imagine staying on a super sandy beach with giant waves. That's going to be pretty tough. So the ocean, and we're going to try this video, and I'm very sorry if it doesn't work, fingers crossed. The ocean is always moving, as we heard from our last talk, with the wind, with the currents, and of course with the tides. And when all of this movement meets land in the intertidal, it can really be quite a collision. This is a video I took just last April off of part of Victoria that I don't think of being super wave swept, but all it takes is a big wind from the south, and with all of that fetch, so that distance, the winds can really kick up. This is a photo from off of Whidbey Island, which I think also illustrates this, because we think of places like the open Pacific around Nea Bay or Port Renfrew as being where you have to think about waves, but even the east side of Galliano, or yeah, the west side of central Whidbey on a windy day, you still, if you're trying to survive in the intertidal, you have to stay very, very attached to whatever surface is available to you. On the other hand, if you're in the more protected areas, so this is again from Denman Island, if you're in those protected bays and inlets that you might be familiar with in the Strait of Georgia or Hood Canal or down by Olympia, getting washed away isn't so much of a worry, but running out of air or food because of the lack of water movement, that might be an issue. So where you'll make it as an intertidal organism will really depend on how much water movement you can or can't take. So now we know a bit about the environment of the intertidal. let's take a look at what intertidal organisms do to make it work. And maybe a good question here to start is, how did they get there? I kind of think about this for this specific sea star. How did this happen? But let's think more generally. What I mean by that is, did the species who live in the intertidal today evolve from land organisms, or did they evolve from ocean organisms? So this is just a really beautiful painting by Tara Camp that I found. If we look at the creatures that we find in this painting of the intertidal, well, actually, if anyone wants to throw in the chat species that they see in this intertidal and recognize, I'd love to see what everyone's familiar with. But if we group them into our more scientific names, mollusks, echinoderms, tunicates, worms, sponges, cnidarians, arthropods, fish, those are all animals. Most of those are invertebrates except for the tunicates and the fish. And then you have our three groups of algae that form seaweeds, red algae, brown algae, and green algae. All of those, all of those, they evolved from marine or aquatic ancestors. That just really leaves the seagrasses and a couple of bugs, a couple of beetles, as the only organisms that you find in the intertidal who actually evolved from that are more related to life on land than in the water. Sorry. There we go. So that just raises some more questions because I can't imagine it's easy for, species to adapt and evolve from spending 100% of their time in the ocean to regularly surviving on land. For one thing, the ocean is reliably, relentlessly, you might say, damp, and land is not. And marine organisms rely on being damp for a whole lot of things. Maybe most importantly, they rely on it for gas exchange, or as animals like us experience it, breathing. So, what are our options for doing this gas exchange in the intertidal if we were originally a marine organism? Well, highly mobile intertidal species, the species that can move around and basically choose where they want to be, those are like sea stars, sea urchins, crabs. They can make sure to stick close to the moist parts of the intertidal. So under rocks, in wet sand and gravel, in tide pools, or basically just below where the tide currently is. And that way, the tissues that they need for breathing, those will all stay moist too. But what about our more sessile, so stuck in one place organisms, or the slow-moving intertidal organisms? So we're talking about things like barnacles, mussels, clams, snails, limpets. They don't have the option to move around and, choose every day what's the moist environment that they want. So what they do, and at the same time, they also still have those gills or other thin tissues that they need to keep moist in order for them to be able to breathe. So what they do is they make hay while the sun shines. When the tide is up, they are breathing all the time. They're taking in whatever oxygen they can get from the ocean around them. But as soon as the tide drops and water is in short supply, they seal themselves off. They seal those thin tissues or gills that they were using to breathe inside of watertight shells. And they keep whatever water they can inside themselves to stop from fully drying out. And then they just wait for the tide to come back. It is holding your breath to like a whole new level. Now, other species, they're a bit more impatient. They don't want to limit themselves to just high tide, or they need more oxygen than the average, tide pool can provide. In this case, things like tide pool sculpins and plain fin midshipmen, which are both fish who spend either long periods, like their whole lives in the intertidal, or important periods, like reproductive periods in the intertidal, they've both evolved the ability to breathe air, which is maybe the coolest solution to living in the intertidal. But it's not something that can last forever. They can only do this breathing for short periods of time, so they actually still do have to stick close to water. Now we've talked about animals. What about seaweeds and marine plants? Not sure how many people are remembering their high school science right now, but of course, plants make their own oxygen via photosynthesis, which uses sunlight to produce energy. But for that process, they need water and carbon. Typically, algae live in water and they absorb carbon directly from seawater. But intertidal seaweeds, they've actually still managed to do this process in air. Species like rockweed and kelps, they continue to photosynthesize while out of the water during low tide. For most kelps, they're less efficient than they would be if they were fully underwater. So they're putting up with it, but as soon as there's water again, they're going to be able to, make more energy, produce more oxygen, be happier. Really interestingly, rockweed actually gets more efficient when they're a little dried out. So they're not only comfortable in the intertidal, they're happier in the intertidal than they would be if they were always submerged, which is quite the adaptation. Now, staying hydrated is not just important for gas exchange. As this very, very sad sea star shows, staying damp is important for generally staying healthy and, in particular, staying cool. One of the biggest stressors for intertidal organisms alongside drying out is extreme temperatures. Now, it sounded like there was a question about water temperature earlier in the last talk. And yes, if you've ever swum in the Salish Sea, you've noticed that even if it looks beautiful, it looks maybe tropical. Everyone loves to call some part of the BC coast the Hawaii of British Columbia every so often. That water is still really cold, and that water will remain cold throughout the summer in most places. The ocean in the Salish Sea, as we heard earlier, stays consistently colder than the air. It also stays consistently colder than the land. And that means that if you're an intertidal organism and it's a daytime low tide in June, you are baking in the sun for hours. That's actually exactly what happened during the heat dome in 2021, when record air temperatures coincided with the tide being out, and we experienced a very unintentional and catastrophic clam bake, or really, mussel bake. So, what do intertidal species of marine origin do to stay cool under these circumstances? Maybe not the heat dome, there wasn't really a lot that they could do in that case, but every single year they're experiencing these daytime low tides with a bright sun and a number of hours out of the water. So, what are they doing to keep themselves from overheating? This photo actually gives a bit of a hint. So, feel free to throw in the chat what you think you see. You may have to stick your face a little bit close to the screen. All right, well, here's the answer. It's basically water being evaporated. So organisms in the intertidal, they use evaporative cooling, which is the same thing that we do when we sweat or that dogs do by panting. Basically, they release heat from their bodies by warming up the water in or around them so much that it evaporates. And that's what you're seeing. It's a really cool thing if you're ever out during a summer low tide and for some reason you're up right at dawn, which is what intertidal scientists do a lot. If you look across the beach, right when the sun comes up and hits, and maybe it's dew from the night, maybe it's the water that's been left behind as the tide has receded, and it's just the dampness of all the organisms. And suddenly you'll just see steam basically coming off of the intertidal, even though it's still quite chilly. So this evaporative cooling mechanism, it's especially useful for organisms that can retain lots of water. Take the aggregating anemone, a common and very beautiful resident of the Salish Sea's rocky intertidal. If you've ever seen them in the water, they're that image on the left. They're beautiful and they're very, very hydrated. Then the tide drops away and they are reduced to sad little blobs that do not live up to the name of a flower, basically. But this, deflation where they're losing water, that actually can help them with this keeping cool process because they have all this water available to them to evaporate off. And that's probably more important than keeping up appearances, if we're honest. Sea sacs, which is a type of red algae, some people call them dead man's fingers. I think that's a little much, but do you know what? It is kind of fun. I'll allow it this time. They also do something really similar. By being tiny water balloons that take in water every time there's high tide, they have this huge reservoir of seawater available to them during low tide for keeping themselves hydrated and also for that evaporative cooling. They avoid getting dried out by just starting every low tide unbelievably hydrated. Now, algae have another trick up their sleeve for dealing with low tides. If you walk out into the intertidal in May, June, July, when it's hot and it's low tide, especially after a string of sunny days, you will notice that the seaweeds, like in this photo, are looking a little bit toasted. To me, they kind of look like a batch of very sad kale chips, except they smell way, way worse. But many of these seaweeds that are getting crispy, they actually can afford to do that. They can recover once they're submerged again. This guy here, the cabbage kelp, my favorite kelp, it, for example, uses these curling, bubbly blades to trap seawater and to shade the base of its body where most of the growth is happening. So you can imagine this as basically a cabbage. You're seeing all the leaves on top, but the part that's actually growing is right underneath at the bottom, and it's anchored, it's also where it's anchored down to the rock. Now, quite routinely, you'll see sea cabbage with huge bits of its blades, this, we call it bleaching, this weird putrid orange color. And those bits of blades are pretty much gone. They're dead. They are going to gradually get sloughed off as the tide washes in after this low tide. But by being able to let those ends die, let that slough off, the bottom bit that they've protected that can still grow just regrows that blade. The blade just continues to elongate. And that means it can survive all of these low tides in a row, basically. Other seaweeds, this one, Pyropia, you might know as nori. This is the seaweed that is used to make sushi. Well, they just withstand extreme levels of drying out that would kill most organisms, including most other seaweeds. So Pyropia doesn't try to prevent that water loss really. It just handles the consequences really, really well. Okay, not to mess with the quiz, but another thing I'd love to see in the chat is whether, like, what percentage of water you think that Pyropia can lose from its body. I'll answer at the end. I think this is going to just be a fun numbers game. So basically, like, yeah, between the photo on the left and the photo on the right, how much of the water has been evaporated? Now, there are still limits to what these strategies can do if deep down you're an ocean organism at heart. Everyone has their limits, intertidal organisms included, so you still have to pick your intertidal home quite carefully. The higher on the shore you live, the longer you will spend out of the water, and the hotter and the drier you will get. So only organisms that can really handle the heat and the drying out can live up there. Typically, those are going to be your barnacles, your periwinkles, those little sea snails, and the small hardy seaweeds like the pyropia we were talking about earlier, nori. Organisms that can't handle as much stress, that need more time in the water, things like kelps, seagrasses, California mussels, they live further down, where they won't experience the stress of low tide as intensely for as long or for as often, sorry. And this is what contributes to the zonation patterns we see. So this is what contributes to the fact that you see those nice bands of different colors when you look at the intertidal. Now, the same patterns around stress actually happen on a much broader scale across the Salish Sea. So closer to the Pacific Ocean, the waves and the cooler weather, plus the fact that summer low tides are actually earlier in the day, that means that conditions are overall less stressful compared to in the interior of the Salish Sea. This means that there are some species which can live in one of these environments, but not in the other. For example, the main mussel found in most of Juan de Fuca Strait is the California mussel, but that pretty much disappears once you hit the San Juan Islands or around the east side of Victoria, at which point the bay mussel, which can handle much harsher conditions, that's what becomes more common. Sometimes you see these patterns at a much finer scale too, and this was something that really came up during the heat dome, where you would see little pockets or patches of organisms that survived when almost everything else died. The thing is, whether you're on a south-facing slope or a north-facing slope, whether you're on a flat bench of rock or on the side of a cliff, that can all affect how much warmth and drying out you're going to experience. The infrared photo on your left has been colored to show the temperature of the rock exposed during an intertidal. I think this is actually in Massachusetts, but we're going to go with it. And what you can see is that the temperature can be 10 to 15 degrees higher on some rock surfaces compared to others. So whether you can survive a hot summer day can change based on really small differences in location. Now, one way of getting around all of this, drying out and warming up, is, of course, tide pools. But not all tide pools are created equally. If your tide pool is higher up in the intertidal, in a warm place with very few waves, you still risk overheating or running out of oxygen. If your tide pool is big and deep, located lower down on the shore, in a cooler, wavier place, you might be okay, but your predator might be too. Keep this in mind. The other thing with tide pools is that they are prime real estate in the intertidal. And the intertidal, like the Pacific Northwest, is in a pretty persistent housing crisis. This brings up another big question about what it takes to live in the intertidal permanently. How on earth do you deal with all your neighbors? This is what the mid-intertidal looks like on an exposed shore. Pretty typically, it's crowded. In the rocky intertidal, space tends to be at a premium, so competition for that space is high. And you need a combination of luck in terms of the timing, in terms of whether a log has recently bashed free some space for you, and also skill to find somewhere to live and then keep that spot for yourself. A lot of species depend on their competitors being more sensitive to terrestrial conditions than they are. So if their competitors have to live lower down on the shore where it's less stressful, that leaves higher up on the shore available for them. And this is the other half of the drivers for these zonation patterns we see. That forms the lower limit of different distributions. So barnacles are the classic example of this, and I want to say a huge thank you to this random cliff off of Souk, which just showed it so nicely, so I was able to get a photo. If you look at the bands of barnacles here, lower on the shore, the larger species of barnacle outcompetes the smaller species of barnacle for space. So you see them forming a dense band. But further up on shore, when it gets too hot and dry for the larger barnacle to survive, it leaves the smaller barnacle in the clear. On top of competition, there are also a lot of hungry neighbors cruising around looking for a snack, just like in tide pools. And that makes choosing a safe place to live pretty crucial. So here is where I took a photo of these beautiful ochre stars. This is just 2023. So I was really happy to see all of these after sea star wasting disease. But if you can imagine, that pile of ochre stars is hungry. And if you zoom in on this photo, you'll see that there are some of its food around, but its food is very far away from where those sea stars are. These mussels are living higher on the shore, where the sea stars that want to eat them can't risk feeding can't go and feed without risking getting really, really hot and possibly roasted to death, essentially. So it's that, again, physical separation that leaves organisms a safe place to live on the shore. Since we're chatting about predation, we should probably talk about food in the intertidal. I've already mentioned that seaweeds and marine plants are photosynthesizers, meaning they're getting their energy from sunlight. but they still do need nutrients. And those nutrients are coming from the seawater, which are replenished by the tide and the waves moving in and out. So again, that's why it's important. If you're a bigger kelp, if you're a bigger organism, it might be hard for you to live in a small tide pool or somewhere where there's not a lot of wave action because you're not getting that replenishment of nutrients all that often. But what about these animals? How are they getting their energy and nutrients? For animals in general, it depends on if you can or can't move, how you're going to be eating. Any guesses at what this organism is? I'm going to check the chat this time. Oh, well, I may have lost the ability to. I'm seeing worm, feather duster. Yes, yes, thank you. I love them so much. We'll go back to my, there we go. Yeah, so this is a feather duster worm, and they are sessile. They are stuck to the substrate. Sorry, I'm just having a fun time with my, there we go. They are stuck to the substrate, so they cannot move to go get themselves food. So like mussels, clams, barnacles, anemones, tunicates, sponges, these are all organisms that can't go fetch their own food. So what they do is they have the food come to them through the water. So they can be called filter feeders, although some people don't like that because some of these organisms aren't really filtering, they're like grabbing, but we're going to go with filter feeders for tonight. They're filtering detritus, plankton, phytoplankton, zooplankton, larvae, all sorts of stuff out of the water, and that forms their food. And then they, in turn, make an amazing food source alongside all those marine plants and algae for the mobile animals that call the intertidal home. So here are some fun mobile critters who are herbivorous. That's things like periwinkles, limpets, isopods, chitons, kelp crabs, and urchins. Uh, in the ocean, when you call something herbivorous, when you say what anything eats, it's always kind of chancy because I find that marine organisms like to eat a lot of things, including unexpected things. So urchins, for example, actually also eat maybe incidentally some meat, but they're mainly herbivores. That's how we tend to think of them. Then there are the properly meat-minded mobile critters like dog whelks, nudibranchs, hermit crabs, moon snails, clingfish, and sea stars, much featured in this presentation. There is actually so much food in the intertidal that it attracts visitors. Plenty of terrestrial organisms that could not permanently live in this environment still want to pop by for a snack. So we've got our Western terrestrial garter snake, who totally ignores its name. It actually loves to check out the intertidal for food. It'll fully swim in tide pools. Here, it's eating a coxcomb, which is an intertidal fish that has an eel-like body, so it kind of looks like it's a snake eating a snake, which I thought was fun. Then, of course, there are mammals. You might have seen these scampering across, well, especially the first two you might have seen scampering across. Mammals in the Salish Sea like mink, river otters, black bears, and coastal wolves. They also like to use the intertidal for food. One of the reasons the intertidal appeals to even these big mammals is while other food sources like salmon and berries are going to be seasonally available, the intertidal is available pretty much year round, and it can make for some spectacular bear watching, I must say. And of course, we can't forget the birds. There are birds like crows, gulls, and bald eagles who have lots of places where they can feed, but they do enjoy a good intertidal meal. I will never be able to explain what seagulls see in sea stars, but other than other sea stars, I swear the most common organism you'll see eating a sea star is a seagull. I don't have a good explanation. Also, apologies to the birders, the gulls. I shouldn't be saying seagulls. Um, the photo of the eagle is actually from Dabob Bay in Hood Canal. And that's a place where bald eagles do regularly spend time in the intertidal, at least once a year. They gather every year to feed on the spawning plainfin midshipman, which is the fish I talked about earlier that can breathe air. And it does seem to be really enjoying that meal It does not look comfortable. That's sitting in an oyster bed. That much must be a little bit scratchy, but worth the food apparently. Then there are also the birds that we really see regularly in the intertidal that might be their main food source. So you've got birds like great blue herons that you'll see in mudflats and estuaries. You have your surf scoters that are out for mussels wherever those happen to be, including on pilings. You have your western sandpipers who are actually going after the basically the scum that forms at the edge of the water, which doesn't sound appealing to me, but I'm happy for them. And then, of course, the black oyster catchers who do not eat oysters. They eat mussels and limpets mostly. The intertidal provides more than just food. For sand lance, which is a forage fish known for its ability to bury its head in the sand, the sandy intertidal is actually perfect for spawning. So that little photo up in the corner shows you some eggs mixed in with sand that they do surveys every year to see where these guys are spawning, and it is largely intertidal. Herring eggs also end up sticking to rocks and seaweed in the Salish Seas intertidal each spring. And there's a really cool two herring talks coming up next week in the Wonders of the Salish Sea series, so stay tuned for those. But I'll give a we'll see if I really hope this video is working. Sorry if you're not seeing much, but this is a video I took of juvenile herring, which also seemed to enjoy the intertidal. This is just a school that was hanging out over what at low tide is a cobble beach with some sea lettuce on it over on San Juan Island. So even when these organisms, it's not their main environment, they still seem to get something out of it. Now, these are organisms that I don't think are particularly frequent visitors, but they do pop in every once in a while. This is a giant Pacific octopus on the left that found its way into a tide pool that I don't think it really wanted to be in during a really low tide. And this is a full-grown adult that was hanging out there and I was really lucky to get to watch. And then on the right, this is another octopus hanging out in the intertidal. This one I couldn't ID super reliably as either a ruby octopus or a giant Pacific octopus. But again, just an amazing place to see these creatures and to remember that the intertidal is just a great place to visit. Being visitors might be our best option too. You have been a wonderful audience, and I believe everyone here is capable of many cool things. I don't think any of us will be evolving watertight shells anytime soon. I also don't think we'll be super successful being baked alive and then tossed through a rising tide twice every day. I just don't see that for us. But I do want to point out that humans have been linked to the intertidal for tens of thousands of years, specifically in the Salish Sea. Many of the nations and tribes who I recognized at the beginning of this talk, I could probably say all of them, they have deep and ongoing relationships with the intertidal ecosystems in their territories. And incredible work is happening right now to restore intertidal habitats in the Salish Sea that are led by Indigenous peoples who have stewarded these places for millennia. This photo is from when Swinomish tribal members visited a clam garden restoration site at Russell Island near Salt Spring in BC. This project is led by Saanich and Hulkaminam nations in partnership with Parks Canada, and it is an ongoing project that has brought a lot of really cool opportunities for Indigenous and non-Indigenous members of the Salish Sea community. I don't have time to cover this topic nearly as much as it deserves, but I do highly recommend you check out these two talks from the Wonders of the Salish Sea series last year about Indigenous-led restoration projects, or you check out these resources for more information on the practice of clam gardening, which is what was shown in that slide before. So very worth your while. So thank you so much for listening, and thank you so much to Transition Salt Spring and the Wonders of the Salish Sea series. I also want to give a quick shout out to Sheila Byers, because this is actually only the second full-length seminar I've ever given, and Sheila Byers was at my first full-length seminar, so I'm very happy to have been here. Thank you so much.
That's too much, Rebecca. That takes me back a bit. It does indeed.